Hello, here is a walkthrough for Pearson Edexcel. It's the physics triple paper, paper 1. You get 1 hour and 45 minutes. It's from 2022, the higher tier. It's worth 100 marks. Question 1. Part A. Which ray diagram shows total internal reflection at an air and glass boundary? Well, total internal reflection is when it bounces back inside, but it still has to have I equals R. And because it's total internal, it has to happen inside the glass, not inside air. So the answer is B. Part B. Figure 1 is a ray diagram for a converging lens when used as a magnifying glass. Part 1. Using information from Figure 1, determine the magnification of the virtual image. Use the equation height of the image divided by height of the object. So just simply measure the height of the image. Now your paper might be different to what it shows on my computer screen depending on my magnification or how much I've zoomed in. So this is the image here, and the height is this, which is 3.7 centimeters on my computer screen, and I'll need to divide that by the height of the object, which is this. And on my computer screen, it's 1.4 centimeters, and that comes out as 2.64. And they said the answer should be 2.6 plus or minus 0.5. So as long as you got that answer, even if these measurements were different, because I'm working on a computer screen, then you've got it correct. Part 2. Describe one way the magnification of the image could be increased. Well, if we use a different lens with a higher power. So that basically means a thicker lens or shorter focal length. That lens there is just skinny, so it's not very powerful. That lens there is thicker, so it's more powerful. Or you could say, move the object further away from the lens. Part C. Figure 2 shows a convergent lens used to produce a real image on a screen. The apparatus is used to find the focal length f of the lens. The screen is moved to give a clear image of the object. The distance from the object to the lens A is 20 centimeters. There we go. The distance from the image to the lens B is 40 centimeters. That's there. Calculate the focal length f of the lens. Use the equation. 1 over f equals a plus b divided by a times by b. So we just need to pop the numbers in first of all. So a plus b will be 20 plus 40, and we need to divide that by 20 times by 40. So that equals 60 divided by 800, and that equals 0.075. But that doesn't equal f, that equals 1 over f. So therefore, if we rearrange that, f will equal 1 over 0.075, and that equals 13.3 recurrent. Question 2, Part A. Which statement describes conservation of energy in a closed system? Well, a closed system means nothing can get in and nothing can get out. Is it A, when there are energy transfers, the total energy reduces? No, nothing can get in and nothing can get out. When there are energy transfers, the total energy does not change. Yep, that sounds about right. When there are no energy transfers, the energy reduces. No. When there are energy transfers, the total energy increases. No. So the answer was B. Part B. The student uses the apparatus in figure 3 to find out which of two materials, sand or sawdust, is the better insulator. The student also has a kettle to boil water, a thermometer and a stop clock. Part 1. Draw a label diagram to show how the student should set up the equipment to investigate which material is the better insulator. Right, well, if we put one can inside the other can and we'll fill this can up with the insulation material and we'll fill this can with water and we'll put a thermometer in there and we'll use a stop clock to time and see how long this stays hot for. So say measure it for 10 minutes, get the starting temperature, get the final temperature, see what the change in temperature was. Then we'll basically repeat it, but we'll change the sand for the sawdust. Part 2. Give 3 factors that the student must control in this investigation. Right, we'd better keep the mass of the insulation constant. We need to keep the volume of water constant. And we need to keep the starting temperature of the water constant. You can also make sure that the time interval that you allow the experiment to run for is also constant. Part C. Expanded polystyrene used to insulate buildings has different densities. Figure 4 shows how the thermal conductivity of expanded polystyrene changes with the density of expanded polystyrene. Using the graph in figure 4, describe how the thermal conductivity of expanded polystyrene changes with the density of expanded polystyrene. So this is the density across the bottom, that's low density, this is high density, and you can see this is thermal conductivity up the side, that's high, and that is low thermal conductivity. So as the density increases, the thermal conductivity decreases. Now that'll only get you 1 mark and it's worth 2. So whenever you see a curve, it doesn't matter which way it curves, you should always say non-linear for that second mark. If it was a straight line, then you say linear. Question 3, Part A. Figure 5 is a speed limit sign from a European motorway. The speeds shown are in kilometres per hour. The sign tells drivers to drive at a slower speed in wet weather. Explain why it is safer for drivers to drive at a slower speed in wet weather. Right, if it's a wet road, there's going to be less friction between the tyres and the road. Which means there'll be an increased stopping distance. Or you could say slower speed means shorter braking distance. And less chance of skidding if you're going slower. I personally prefer the blue explanation. Part 2. Show that a speed of 31 meters per second is less than a speed of 130 kilometers an hour. Right, let's convert meters per second into kilometers per hour and see how much it comes out at. So if you're doing 31 meters per second, let's divide that by 1,000 and that'll tell us how many kilometers per second you're doing. So that's 0.031. Now we want to know how many kilometers per hour. So if we multiply that by 60 seconds per minute and then multiply it by 60 again, because there's 60 minutes in an hour, then that'll tell us how many kilometers per hour. So that's 111.6 kilometers per hour. So we've just proved that 31 meters per second is less than 130 kilometers an hour. It's only 111.6 kilometers per hour. The other way you could have done it is to convert from kilometers per hour into meters per second. The way you would do that is you'd take 130 kilometers per hour. Now if we multiplied that by 1,000, that'll tell us how many meters per hour. So that's 130,000 meters per hour. But we want meters per second. So we then have to divide that by 60 times by 60. And that equals 36.1 meters per second. And they said, show that a speed of 31 meters per second is less than a speed of 130 kilometers per hour. It is. 130 kilometers per hour is 36.1 meters per second. So that is less than that. Personally, I prefer to do it the blue way. Part 3. The driver's reaction time is the time between the driver seeing an emergency and starting to brake. So seeing the emergency is what we'll call the stimulus, and starting to brake is what we call the response, and the time between the stimulus and the response is the reaction time. A car is travelling at a speed of 31 meters per second, that's our speed. The car travels 46 metres, that's our distance, between the driver seeing an emergency and starting to brake. Calculate the driver's reaction time. So we want the time. Give your answer to two significant figures. So what formula do we know that relates speed, distance and time? Speed equals distance divided by time. We're after the time, so let's rearrange that using a magic triangle. Distance would go on the top because it's on the top out here, and then speed times by time. Cover up time, what are we left with? Distance divided by speed. So time equals distance divided by speed. Let's pop the numbers in. The distance was 46 metres. The speed was 31 metres per second. And that comes out as 1.4387. And they wanted it to two significant figures. So the first significant figure is the first figure that's not a 0. So that is the first figure. That's not a 0. So that's the second significant figure. And this 8 turns the 4 into a 5. So the two significant figures, the answer is 1.5 for 3 marks. If you left it as 1.48, you would get 2 marks. Question 4, Part A. Radioactive traces can be used when scanning a person's kidneys. A radioactive isotope is injected into a person's bloodstream. The isotope emits radiation. As the blood flows through the kidneys, this radiation is detected outside the body by a scanner. What type of radiation travels from the kidney to the scanner? So you're looking for something that's very penetrating. So it wouldn't be alpha, that wouldn't get outside. You wouldn't put beta inside someone either. Any kind of beta. So the answer is gamma. You would only ever inject gamma into a person because it's very penetrating. It can easily get out without causing damage because it's got low ionization powers. Alpha is very ionizing. You would never inject that into a person. And beta would do more damage than gamma as well. Part 2. During the scan, a technician needs to take readings for about 30 minutes. The half-life of the isotope used is about 6 hours. State why an isotope with a half-life of about 6 minutes is not suitable. Well, it decays too quickly to give a reading. Or to get a result. In other words, the half-life is too short. Part 2. State why an isotope with a half-life of about 6 days is not suitable. Well, that half-life is too long and it would stay in the body for too long. It could cause damage to the body. Could damage the patient. They'll get too high a dose of radiation. You only need to say this bit in red in order to get the mark. Part 3. State 2 ways of reducing the radiation risk to the technician. Right, if you're the technician giving it to the patient, you want to use shielding. Usually lead. Like a lead apron, something like that. You could use tongs to pick it up. Other things you could say is limit the time that they are exposed for. Get them to stay away from it as much as possible. They could use a dosimeter badge to monitor exposure. They could store the source in a lead box. Any of those. Again, I like the answers in the blue. Question B. Figure 6 is a diagram of a nuclear reactor. Part 1. Explain how pushing the control rods further into the reactor slows down the nuclear chain reaction. Right, the control rods would absorb the neutrons. So fewer neutrons are available for a chain reaction. Remember, your little neutron goes in and it hits your uranium nucleus. That uranium nucleus splits up into 2 smaller nuclei plus 2 or 3 extra neutrons would be given off, as well as the energy. Now, by dipping the control rods down, now they're usually made of boron or graphite. They'll absorb these neutrons, so these neutrons are not available to go on to strike more uranium atoms. That is what the chain reaction is. Part 2. The moderator in a nuclear reactor slows down the neutrons so that the neutrons are more likely to start other fission reactions. So the moderator is something like heavy water. In a nuclear reactor, The average speed of the fast neutrons is 3 times 10 to the 7 meters per second. The average speed of the slow neutrons is 4 times 10 to the 3 meters per second. Calculate the average speed of the slow neutrons as a percentage of the average speed of the fast neutrons. So you just need to do the slow neutron speed divided by the fast neutron speed. And if we want it as a percentage, you'll need to multiply it by 100 to get it into a percentage. So let's pop the numbers in. The slow speed was 4 times 10 to the 3 meters a second, and we'll divide that by 3 times 10 to the 7 meters per second, multiply it by 100%, and that comes out as 0.013 recurring, 333%. Part 3. The nuclear reaction is the first stage in the process of generating electricity. Describe how energy is transferred from the nuclear reactor to the next stage in the process. So, what type of energy is involved in a nuclear reaction? That would be nuclear energy. And that would get transferred into thermal energy. Remember, we're just trying to create heat to boil water into steam so the steam can turn a turbine and the turbine can turn a generator. So a nuclear power station is basically like a coal, oil and gas power station. It's like a giant kettle. We're just trying to boil water into steam. Question 5. A part 1. An aircraft starts from rest and accelerates along the runway for 36 seconds, that's the time, to reach takeoff velocity. Takeoff velocity for this aircraft is 82 meters per second. Show that the acceleration of the aircraft along the runway is about 2 meters per second squared. Assume the acceleration is constant. So that's our acceleration. That's the takeoff velocity, which will be the velocity at the end v. And it says it starts from rest, that'll be u, and if it's from rest, that means 0 meters per second. Show that the acceleration is that, so even though it gives us the acceleration, we have still got to work that out to prove that it's 2. So acceleration is v minus u over t. So the final velocity v was 82 meters a second. Take away u, which was 0 meters per second, and divide that by the time, which was 36 seconds. And that comes out as 2.27 recurring meters per second squared. That's 2.3. Part 2. Calculate the distance the aircraft travels along the runway before takeoff. Use the equation v squared minus u squared equals 2ax. So x is the distance, so that's our target. So it's best to pop those in brackets when you're rearranging, because that's one thing, take away another thing. We can just keep those together as we rearrange. So we need to get x by itself, so if we just divide both sides by 2a, then that'll cancel out the 2a on this side and just leave x. So x will equal v squared minus u squared divided by 2a. We'll pop the numbers in. So you could have just put 2.3 there, but old habits die hard. At A level, you'd never round up if it's part of a calculation. And that equals 1,476. And that's meters. If you used 2.3, instead of 2.277777, then that would have came out as 1461.7. Part 3. Suggest one reason why the length of the runway used is always much longer than the calculated distance that the aircraft travels along the runway before takeoff. Right, it's just in case you need to sort of abort the takeoff, or if there's some kind of mechanical engine failure. There could be some weather-related reasons that might cause your acceleration to be reduced. Like if the runway was wet, that would slow your acceleration down. You might have a heavier plane due to extra passengers or extra luggage. Or you might need a longer runway for the landing. Any of those will get you 1 mark. B part 1. The aircraft lands with a velocity of 71 metres per second. The mass of the aircraft is 3.6 times 10 to the 5 kilograms. Calculate the kinetic energy of the aircraft as it lands. So kinetic energy is our target. Right, let's use the equation for kinetic energy. That is 1/2 times by the mass times by the velocity squared. Pop the numbers in. And that equals 90738000, which is 9.07 times 10 to the 8. Or you could say 9.1 times 10 to the 8. That's fine as well. Part 2. When the aircraft has come to a stop, all the kinetic energy has been transferred to the surroundings. Give one way that the energy has been transferred to the surroundings. Well, it'll be as heat. Thermal energy. If they say why, you would say due to friction. If it was worth 2 marks instead of just 1. Now, for some reason, they're not actually accepting as sound. I'm sure there would be a bit of sound, but always go for heat first anyway. Question 6, Part A. The Big Bang and steady state are 2 theories of the origin of the universe. Redshift and cosmic microwave background radiation have been discovered by observing the universe. Which line of the table links the evidence to the theory it supports? Right. The redshift is evidence of an expansion, which both theories support. So the Big Bang theory says that the universe is expanding, so that could be right. Steady state says that it's expanding. That's a yes. That's a yes. That's a no. So straight away, we know that D's wrong. And the cosmic microwave background radiation is evidence of a bang. Does the Big Bang theory have a bang? Yeah, obviously. So that's wrong because it said no. Steady state, does that have a bang? Nope. The steady state theory states that the universe has always existed and there never was a bang. Big Bang theory, yes. There's obviously a bang. And that steady state says yes, so that's wrong. So the answer is C. Part B. Figure 7 shows 2 hydrogen spectra. One spectrum is taken from a source on Earth. The other spectrum is taken from a source on a distant galaxy. The spectral lines in the spectrum from the distant galaxy are shifted towards the red end of the spectrum. So this distant galaxy here, all the lines from there have been shifted over to the red end of the spectrum. The wavelength of line X on Earth is that. The wavelength of line X from the distant galaxy is that. The redshift Z is given by the equation that. Part 1. Show that the redshift for the light from the distant galaxy is about 0.025. So we just basically need to pop the numbers in. So wavelength of the G, distant galaxy, 6.72 times 10 to the minus 7 meters. We need to take away the wavelength from Earth, 6.56 times 10 to the minus 7, and we need to divide that by the wavelength of line X on Earth, and that equals 0.024390. It said show that it's about 0.025. Yep, it is. Part 2. The galaxy is moving away from the Earth at velocity v, the recession velocity. The velocity of light c is 3 times 10 to the 8 meters a second. The recession velocity is given by the equation v equals z times by c. Calculate the recession velocity of the distant galaxy. So we just need to pop the numbers in. So Z we've just calculated was 0.024. I like to put the full number in, and then we'll multiply that by the speed of light, 3 times 10 to the 8, and that comes out as 7317000 meters per second. So that's 7.3 times 10 to the 6 meters per second. If you'd used that value as just 0.024, then your answer would have came out as this, 7.2 times 10 to the 6. So either of those values are fine. Actually, if you'd used their value as 0.025, then that would have came out as 7500000. So 7.5 times 10 to the 6. So that would have also been accepted. Part 3. The wavelength of the spectral line X measured for a more distant galaxy was 6.92 times 10 to the minus 7 meters. Explain how this provides evidence that the universe is expanding. So basically, if that's the Earth, if something is moving away from us, the redshift value would be small or smaller than something that was further away from us and moving faster. Because if everything started from a single point, according to the Big Bang, then if something is further away, it must mean that it's faster. So the redshift value is bigger, proving that it is moving away faster. So the redshift value is bigger, proving this more distant galaxy is moving at a higher velocity, which is consistent with the Big Bang theory. Part C. Observations of the universe can be made using telescopes on Earth. Explain why some telescopes are located on satellites that orbit the Earth. Right, well, a good thing about that is if the telescope will be outside of the Earth's atmosphere, so there's less interference from dust and clouds, things like that. Or just general atmospheric distortion. Something else you could say is that you would be able to see more wavelengths of light and other electromagnetic waves that would have otherwise been absorbed by the Earth's atmosphere. And you can basically view the whole sky, rather than just a portion of the sky from a Earth-based telescope. One thing they wouldn't accept is you saying that the telescope is closer to the object in space. Yes, it would be, but the relative closeness is absolutely nothing compared to how far away it is anyway. It would be like you trying to see something 10 miles away and taking one step closer and thinking that you're going to be able to see it a lot better. Question 7, Part A. Which of these is a unit of momentum? Right, momentum equals mass times by velocity. So that's kilograms multiplied by meters per second. So that's kilograms, meters per second. That's correct. That one, A. I like to put the little dot in between just so it sort of separates the units. Part B. Students investigate conservation of momentum using two identical trolleys. A cord is then added to trolley A. Some of the apparatus is set up as shown in figure 8. Part 1. Describe an investigation the students could carry out to show that momentum is conserved when these two trolleys collide. You may add to the diagram to help with your answer. Right, well, whenever we've got conservation of momentum, let's start with the formula for momentum. So momentum equals mass times by velocity. Now you'll sometimes get a mark just for saying that. But what the formula does do is it tells you what you need to measure. So we're going to need to measure the mass of the trolleys with what? With a mass top pan balance. So we might get a mark for that, we might get a mark for that, we might get a mark for that. We're going to need to measure the velocity before and after the collision. Now, how are you going to measure the velocity? Do that with a light gate. Now, you'd have to put a light gate here, and you'd have to put another one over here before and after the collision. And because the saying momentum is conserved, you need to make sure that you tell the examiner you know what that means. It means the momentum before the collision equals the momentum after the collision. And if in doubt, just put the good old trusty repeat and take an average. So it's always the same pattern. 1, 2, 3, 4, 5, 6, 7, 8. Potentially 8 marks for a 4-mark question. I think they're being a bit tight with the marks there, because personally I wouldn't leave out any of those instructions if you're going to do a complete method. Part 2. Give a reason for the runway being at a slope. So if you'll notice, the runway is just on a very gentle slope. And the reason for that is so that the trolley A would just start to roll, but it wouldn't accelerate. And what that means is you have managed to reduce the effect of friction, which would mess up your results. To reduce the effect of friction, it cancels out friction, or you could say the purpose of that, so that trolley A travels at a constant speed. If it's only worth 1 mark, I like to say the blue thing about friction. If it's worth 2, I'll say them both. Question C. Figure 9 shows a racket and a tennis ball. The tennis ball is travelling toward the racket at a velocity of 8.2 metres per second. The ball is hit back in the opposite direction at a velocity of 15 metres per second. The ball has a mass of 0.075 kilograms. The ball is in contact with the racket for 12 milliseconds. Right, so that's 12 times 10 to the minus 3 seconds. Because milli is times 10 to the minus 3, 1,000th. Part 1. Calculate the average force exerted by the ball on the racket and use the equation. F equals final momentum, take away the initial momentum, divided by the time. Now you're going to have to decide which way is positive and which way is negative. Because if we're dealing with velocity, that's a vector, so direction's important. So if we say that as the ball's coming in, that's a positive velocity, then as the ball's going back out to the right, that'll be a negative velocity. So we'll pop the numbers in. So the mass 0.075 times by the final velocity, which will be minus 15, and we need to take away the mass times by the initial velocity, which was a positive 8.2, and we'll divide that by the time, which was 12 times 10 to the minus 3, and that comes out as minus 145, and that'll be newtons. Now all that the negative sign means, remember, in the world we've created, negative just means to the right. But they're not interested in the direction, so you can just put 145. Now, what if you think, what if I'd said to the left was negative, which means to the right was positive? Right, let's pop the numbers in and I'll show you. So that 15 will be positive this time. And it'll be the 8.2, that's negative this time. And that equals 145 newtons. And because it's positive, we know in this world, the red world, positive means to the right. So once again, 145 newtons to the right. So it doesn't matter which way round you assign positive and negative. You still end up with the same answer, just in case you were wondering. Hope that helps. Part 2. Describe how Newton's third law of motion applies to the collision between the racket and the ball. For 2 marks. Easy peasy. The forces will be equal in size, but opposite in direction. If it was worth more than 2, you'd say the forces act on 2 different bodies. i.e. the racket and the ball, and you'd say that they are both the same type of force. So obviously the ball is putting a force on the racket and the racket is putting a force on the ball. The forces are equal in size but opposite in direction. Question 8, Part A. Rutherford devised an experiment to fire alpha particles at thin gold foil. It was found that alpha particles were scattered by the gold foil. The gold foil was about 4 times 10 to the minus 7 metres thick. A gold atom has a diameter of about 0.15 nanometres. Estimate how many gold atoms would fit across the thickness of gold foil. So 0.15 nanometres is basically 0.15 times 10 to the minus 9 metres. So we've just ripped out the nano and replaced it with times 10 to the minus 9. That's all you do. Now, how many of these will fit into that? Let's have a look. And that equals 2666.66 recurring. And we'll just round that up to 2,667. Part B. The apparatus that was used in the experiment is shown in figure 10. Right, it's a usual gold leaf experiment or alpha scattering experiment where you fire alpha particles at the gold foil and particles can go straight through, so zero deflection, or it could be deflected up by any angle or down by any angle, or it could even come right back where it came from. Part 1. The number of particles detected at each angle in a given time is shown on the graph in figure 11. Use information from the graph. Estimate the ratio of the number of particles scattered through 5 degrees to the number of particles scattered through 100 degrees. So when they're talking about a ratio, you can just do one thing divided by the other thing. Right, 5 degrees. So there's the scattering angles there. That's 0 and that's 20. That'll be 10. So 5 will be about there. And if that's 10 to the 6 and that's 10 to the 7, then that is going to be about 7 times 10 to the 6. So if you imagine 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. And right, this is a lot easier. Scattering angle 100. That is much straightforward. That's just basically 1 times 10 to the 2. So if you didn't understand what these mean, 10 to the 3 actually means 1 times 10 to the 3. And then if that's 1, then that would be 2 to the 2, 3 to the 2, 4, 5 times 10 to the 2, 6, 7, 8, 9, and then up to the 1 times 10 to the 3. So we just need to do that number divided by that number. And that equals 70,000. Now they will accept any number between 10,000 to 100,000. Now the other way you could do it as a ratio is you could just do 1 times 10 to the 2 to 7 times 10 to the 6. And if you divide both sides by the smallest number, which will be 1 times 10 to the 2, well, that divided by that will give you 1, and that divided by that will give you your 70,000. So you could express it like that, 1 to 70,000. Part 2. Explain how the difference in the number of particles scattered at different angles gives evidence for the current model of the structure of the atom. Right, let's go back up and have a little look and see what's going on. Right, what they're saying is that you've got a lot of particles that pretty much came straight through. So most particles passed straight through. With little deflection. Right, some particles have been deflected at angles between 20 and 80 degrees, 20 and 100 degrees. So some particles sort of bounced around this area. And not many particles were scattered more than like 100 degrees. So that would have mean they've hit off here and then literally bounced back. Now, what does that evidence suggest? Well, it took Rutherford himself about 2 years to understand what these three pieces of information meant. Most alpha particles pass straight through the gold with little deflection, so that means that most of an atom is empty space. Some particles were deflected or scattered at angles between 10 to 90 degrees. Now they know that an alpha particle is positively charged. So what that means is that if it's been deflected, the alpha positive must have came close to something else that was positive. The atom must have a positive centre or nucleus that repelled the positive alpha particle. And the fact that very few alpha particles were scattered or deflected by angles greater than 90 degrees means that the nucleus, the positive nucleus, must be very small and is hard to hit, because it'll only bounce back at greater angles than 90 if it's kind of on a head-on collision. So if this is the gold foil, and that's the little positive nucleus in the middle, when you fire the alpha particle, the positive alpha particle, most of them go straight through at 0 degrees. That's because they're not anywhere near the nucleus. Now, if you do start to get close to the nucleus like that, wallop, then you'll be deflected at angles, you know, of sort of 45 degrees. Get a little bit closer, boom, and you're up to there. Now, for the alpha particle to come back at angles greater than that, it must hit it kind of head on, and that doesn't happen very much. To come back at angles greater than 90 degrees. Pyong. So I hope that helps you to understand. This could easily be 6 marks, and that statement goes with that goes with that, and that goes with that. So the blue is the evidence and the red is what it means. You'd get a mark for that, and that. So you can say any 4, since it's only worth 4 on this occasion. Question C. Students are given the apparatus shown in figure 12 and a protractor. Part 1. Describe how the students could use the apparatus to model the scattering of alpha particles. Right, well, it's as I've said. If this marble here acts like the alpha particle and this circular weight here is acting like the nucleus, then if you move this slope, say up to here, and you basically fire it down, that's going to be a deflection of 0 degrees, 0 degrees, 0 degrees. Now once you sort of clip it there, boink, then it's going to be, you know, more than 0 degrees, but kind of less than 90. So I'll just say 45 degrees. Now as you bring it down here and it hits there, doink, now it's going to come at greater than 90 degrees. And if you hit it head on like that, bang, it's going to go at, you know, what's this, 135 degrees. So that's how you can use this as a model of the alpha scattering experiment, otherwise known as the gold leaf experiment. Roll a marble down the slope so it kind of behaves like an alpha particle, and then basically record where the marble goes, or measure the angle of the path. Saying either of those is fine. Part 2. Give one limitation of this model. Now it's only worth 1 mark. There's tons of stuff you could say, but I think the best things to say is that the marble doesn't actually have a charge, like what the alpha would, and the weight doesn't have a charge, like what the nucleus would. And what that means is for the deflection to happen, it's actually going to have to hit. The marble is actually going to have to hit the weight, whereas in real life, the alpha particle wouldn't actually have to hit the nucleus in order to be deflected. You'd have repulsion as it approached. And obviously, nothing is to scale. Question 9. This question is about waves in the electromagnetic spectrum. Part A. The potential danger associated with the waves of the electromagnetic spectrum increases as frequency decreases. No. Frequency increases. Yes. So a low frequency would be like that, not going up and down very often. That doesn't have much energy, it's not going to do much danger. Whereas if the frequency increases, alright, it's going up and down, up and down, up and down a lot. So it's got a lot more energy. So that's going to do you some danger. And the velocities is just an ambiguous distractor. It's just put there to try to put you off. So what you're looking for there is, as the frequency increases, the energy would increase. And that is when it's dangerous. High energy or high frequency. B1. A microwave oven uses waves of frequency 2.45 gigahertz. Right, so that's 2.45, and we'll cash in the giga and we'll exchange that for a times 10 to the 9. So that's what gigahertz means, times 10 to the 9. And then we'll just stick the hertz on. Calculate the wavelength of the microwave. So wavelength is our target. That's the frequency. The velocity of light is 3 times 10 to the 8 meters per second. So we know the velocity. Right, so the formula is velocity equals frequency times by wavelength. Let's pop that into a magic triangle because we need to work out the wavelength. There's room for something times by something, and it's f times by lambda, so let's shove that in. and V must go on the top, cover up what we're looking for, which is the wavelength, lambda, and we're left with V divided by F. So wavelength equals wave velocity divided by frequency. Pop the numbers in, and that equals 0.122 meters. Part 2. The microwave oven is 55% efficient and transfers 42,000 joules of energy to some food when it's heated. Calculate the total amount of energy that must be supplied to the oven. Well, the easiest way to do it is 55% equals 42,000 joules. So if we divide both sides by 55, that'll tell us what 1% is. 763.63636363. If we multiply both sides by 100, then that'll give us 100%. 76363.6 joules. 76,363.6. Question C, a 6 marker. X-rays and radio waves are part of the electromagnetic spectrum and have different uses. These radiations are produced in different ways. X-rays are emitted when electrons within an atom go through energy changes. Radio waves are produced by electrons in circuits. Compare X-rays with radio waves. Your answer should refer to the uses of both types of radiation and the different ways that electrons are involved in producing X-rays and radio waves. So we'll split it up into X-rays and radio waves. Right, let's give uses of both of them. So X-rays used for checking for broken bones. You could say treatment of cancer, airport security, looking inside bags. Right, radio waves used for broadcasting radio, broadcasting TV, just generally communications. Right, what about how they're produced? Right, so there's your nucleus, there's your shells. Now there's an electron in a shell. Now if that electron absorbs energy, that electron can jump up into a higher shell. And when that electron eventually drops back down, the energy it emits is how it creates the X-ray. So how do we write that? An electron or electrons in lower shell absorbs energy, jump to a higher shell, and it emits the X-ray when it drops back down the shell. Now it would need to lose a lot of energy because X-rays have got a lot of energy. Right, what about radio waves? How are they created? Or how are they produced, as the question said? So you've got alternating current flowing in an aerial, metal aerial, produces the radio waves in the air around the aerial. and the radio waves would have the same frequency as the frequency of the alternating current. So how many times per second the little electrons go up and down inside the aerial, say 50 times a second, that would create radio waves of 50 hertz. Remember, however many hertz it is, that tells you how many times per second it's alternating. Right, you'll easily get your 6 marks. Just make sure you say something from this part, this part, this part, and this part, and then double up in a couple of areas. Question 10, Part A. The human ear can only detect frequencies below ultrasound and above infrasound. Which of these gives the approximate range of frequencies for the human ear? So ultrasound is 20,000 hertz and infrasound is anything below 20 hertz. So the answer is B. Mind, I don't like the way they've said 20 kilohertz to 20 hertz. I think the lower number should have been at the bottom. So it should have said 20 hertz to 20 kilohertz. I don't know if they've intentionally tried to be a little bit awkward there. So just watch out for that. Part 2. Suggest 2 reasons why there are limits to the frequencies that a human ear can detect. So basically there's the lug. And then there's your ear canal. You've got a little eardrum there, which is a thin membrane. Then you've got sort of 3 little bones, the hammer, the anvil and the stirrup. And then you've basically got a sort of snail-like structure, which is your cochlea. And that's full of sort of little hairs that vibrate and send a signal down the auditory nerve. So you could have the size of the parts of the inner ear or a limiting factor. You might say, what's the inner ear? Well, all of that stuff, the stuff that's inner. This bit here would obviously be the outer ear. Now you can see on the side of people's heads. Now this membrane thickness of the eardrum, if it's stiff, that is a factor. You've got different parts vibrating at different frequencies. They might not all be able to keep up with each other, and the brain just cannot interpret low and high frequencies. Part B. Ultrasound can be used to find cracks in metals. Figure 13A shows the signals emitted and received when the metal bar has no cracks. So that's this part here. You've got one signal as the sound goes in, and you've got another signal as it hits the far side and comes back. Figure 13B shows the signals emitted and received when the metal bar has a crack. So once again, you've got the 2 signals like you had before. One of them is immediately, because there's a reflection off the front surface, that signal R is the reflection off the back surface. Now you've got this new signal Q, which is a reflection off the crack. Whenever there's a change of density, you're going to get a reflection. So you've got a change of density at the front where the air meets the metal, change of density at the back where the metal meets the air, and if there's a crack in the middle, that's going to have a little bit of air in as well. So you've got another change of density there. So reflection 1, reflection 2, reflection 3. That's reflection 1, reflection 2, reflection 3. Whereas here you just had reflection 1, reflection 2. Reflection 1, reflection 2. Part 1. Explain how the signals in figure 13A and 13B show that there is a crack in the metal bar in figure 13B. So if we say this is the base of the metal, which would be this reflection here and this reflection here, and remember 1 was the upper surface. This reflection 2 has happened before reflection 3, so it means I'm getting a reflection before the sound gets down to the base of the metal. So signal Q is a reflection of ultrasound off the crack before signal R, which is the reflection of ultrasound off the base. Part 2. Suggest one reason why the amplitude of signal R in figure 13B is smaller than the amplitude of signal P shown in figure 13A. Right, so the amplitude is the energy, and that's got high energy, whereas here it isn't as high energy. That's because some of the energy has been absorbed by the crack. Signal R is less than signal P because some energy has been absorbed by the crack, which was signal Q. Or instead of absorbed, you could have said reflected. That would be fine. Question C, the last question, another 6 marker. The table in figure 14 gives information about seismic waves, S waves and P waves, produced by an earthquake. So S waves are transverse, P waves are longitudinal, S waves are slower, SS, P waves are faster. S can travel through solids, whereas P waves can travel through liquids and solids. Figure 15 shows the paths of some S waves and P waves coming from an earthquake, the type of wave detected in different regions, A, B and C, of the Earth's surface. Explain what the diagram in figure 15 shows about the density of the Earth and the nature of the Earth's core. Use information from the table in figure 14 and the diagram in figure 15 in your answer. Right, let's break our answer down according to section A, B and C. So at section A, we've got P and S waves are detected. Now, S waves can only travel through solids, so that would suggest that this area here must all be solid. So longitudinal and transverse waves are both detected. So this part of the Earth must be solid. And the P waves are faster than the S waves, so the P waves would arrive first. Now, because there's a slight bend or refraction, that must mean that the density is changing as you go deeper. So a gradual refraction of waves, so there must be a gradual change in density of the Earth at that point. Now at point B, there's no waves being detected. Now that must suggest that this part of the Earth's core is liquid. So that's why the S waves can't get there. And the fact that the P waves can't get there either, now that's because when you've hit this part here, there was a sudden change of density, and that caused the wave to suddenly change direction. And then there's a sudden change of density there, which makes it suddenly change direction again. And that left what we call this shadow zone. So there must be a sudden change of density when it hits the Earth core. Sudden change in density of core caused a sudden refraction of the P waves, so none arrived at section B. And section C, P waves have been detected, but not S. So once again, that would suggest that the Earth's core is liquid and the S waves can't get through. No S waves arrive, so the core is liquid. Now that is enough information, or enough answers, to get you 6 marks. Now there are other things that they will accept, such as some of the P waves would arrive here before some of the other P waves, depending on which path through the core it's gone. These P waves here have actually gone through the central solid part of the core, so they would travel faster and arrive quicker than P waves that have just gone through the liquid part. But personally, I don't think that's fair for them to accept that, because how would you know based on the information they've gave you? So I think this answer here in red's a bit sketchy. So that basically proves that the inner core is solid. One, 2, 3, 4, 5, 6, 7. There's 7 good statements there, so you definitely get your 6 marks. And that's the end of the paper. Now, the more of these papers you practice, the better you'll get. And that's a fact. Your scores will increase with purposeful practice. Good luck in your summer exams. Work hard, be nice, and bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.